Hey folks, Todd Coburn here with the Aerospace Structure Series. This is part of our Mechanics of Composites course, and we're going to focus today on the strength of sandwich structures. Let's see how it works. So we saw last time that we characterized our sandwich structure as a lumped section, like we did back in our Structures 1 class with lumped areas of beams. And in this case, our face sheets are carrying all normal loads and also all in-plane shear loads. We saw that our core was only taking the transverse shear loads and that our core provides continuity between our face sheets so they act as a single bending member. We developed our simplified bending model following this approach, and we introduced some nomenclature so we could tell specifically our H parameter, which is the distance between the midplanes of the face sheets, and we calculated our stresses on that basis in the face sheets. You'll want to review the last lecture, lecture 13, if you need to refresh in those ideas. And we now can write our margin of safety on that. And now to write the ultimate margin of safety on the face sheets, we're going to go and take that maximum stress, which is either tension or compression in the two face sheets, and we're going to compare that to the allowable, the FTU or FCU of the face sheet. Now, while this is actually appropriate for tension stresses, and it also is appropriate for compression stresses, we're going to find out that for sandwich structures, this is almost never the critical margin of safety. There are usually many lower margins of safety from other failure modes that sandwich structures are characterized by. But we should never forget that we also need to make sure that we don't exceed the ultimate allowables of the face sheet, and this would be how we would check. And we could check any in-plane shear stress in the face sheet against the FSU of the face sheet as well. Okay, so these checks are checks we need to make, but they're ones that will typically not be the most critical ones. So that's the margin of safety for tension and compression on that basis. The next idea is shear crimping. This is a very common failure mode for sandwich structures. This shear crimping occurs when we have compressive load, axial compressive load on the sandwich. It's a localized failure mode. It's caused by low density of the core material, and it's characterized by a sudden shear failure in the core. You want to see that again? It's characterized by a sudden shear failure in the core. You're compressing the composite or the sandwich, and it suddenly fails in shear with a lateral translation of the thing, a short lateral translation. That's what a shear crimp looks like. And it's usually the margin of safety is usually written on a running loads basis. So we're going to calculate the running load in the face sheet, in the sandwich, and we're going to evaluate shear crimping. Typically, a 75-ish% knockdown is used. Actually, typically maybe too strong of a word, but it's very common to use a knockdown on the allowable, and 75%. Not a 75% knockdown, but a 25% knockdown, so we're getting 75% of the allowable. So we can calculate our shear crimping allowable like this. It's h squared over the thickness of this core times the shear modulus of the core times, if you're using a knockdown factor, what that is. So that means we're getting 75% of that allowable using this approach. This is the approach we used on the Delta family of rockets. Our margin of safety then is written by just comparing our allowable shear crimping running load against the actual compressive running load. This is never written against tension, only against compression. Our next failure mode is called face sheet wrinkling, and this is also a localized failure mode. It's influenced by low bending stiffness of the face sheet and also low stiffness of the core. This has the idea of your face sheet when it's in compression and it's sitting on this foundation, this core that has a stiffness, and that core is holding it in place. If that face sheet were compressed because it's so thin, it would buckle in Euler buckling at a very low load. And what that core does is it adds stiffness to drive it into higher modes, second, third, fourth, fifth, and much higher modes depending on the stiffness, as long as it doesn't fail. It's like crowd surfing. Imagine the face sheet hurls itself on the crowd of the core material, and all the core material is just carrying it up with its little fingers. And if any of the little core material has got a low stiffness, then the face sheet can buckle down into there. Kind of analogous to a little bit kind of like your inter-rivet buckling allowable that we studied in our Structures 2 class. So this is characterized by deflections, little depressions in the face sheet. Often it looks like somebody shoved their thumb down into the material or bubbled up the material. Now, I'm showing one of these where we see crushing of the core and another one where we see failure of the core, but the core doesn't necessarily need to fail for this to happen. It just needs to be pulling away and such that the face sheet can continue to deflect, and that will eventually cause a failure as well. We usually write these on a stress basis, and I have experienced a number of different ways to develop this from many different resources, including some that folks that I work with have developed. I'm going to go ahead and present this equation from Brune, which is 43% of the modulus of the face sheet, core, the shear stiffness of the core, L to the 1/3 power. So we can use this to approximate the face sheet wrinkling allowable for composite, for any kind of sandwich. Now, one thing to remember, this is actually for a flat face sheet. If your face sheets are flat initially, this is what the allowable is. If you have an initial dimple, then there are other methods to try and develop what that is. And we also did a bit of work on that too. I may present some of those in the future. Our margin of safety then, once again, is going to be comparing this face sheet wrinkling allowable to the compressive stress in the face sheet. So usually we're going to write this on the basis of one face sheet, whichever face sheet. If we have compression, both face sheets are under equal compression. If we have bending, one face sheet is under compression. We could calculate the mid-plane stress in that face sheet and then write the face sheet wrinkling allowable and then margin of safety on that compressive face sheet. The next failure mode is called face sheet dimpling. It's also a compressive failure mode. It's also a localized failure mode. This failure mode only occurs when we have honeycomb-like structures where we have support of the face sheet, but it's not completely continuous. So honeycomb has voids. So we have cell sizes, and that means we have the face sheet is unsupported over some small distance. So in a manner similar to in-rivet buckling, we can see that face sheet buckling out. So it is a localized failure mode. It's influenced by, once again, the bending stiffness of the face sheet, which is resisting that, but also that unsupported dimension of whatever the core material is. And it's characterized by dimples in the face sheet, kind of like this, where these dimples in the other case, for face sheet wrinkling, the dimple could be any size. In this case, that dimple will be about the cell size of the underlying core material. So if we have a hexagonal core, we'll take the distance between the flats as our S dimension. If we have a square core size, some kind of honeycomb that's made with square cells, then that would be the flats once again. And we usually will write this also on a stress basis. So this is one common relation for this, where we take the face sheet thickness divided by that cell, the flat distance between the flats of our cell, right? So we're talking about, we have honeycomb and we got the face sheet. So whatever the size of that honeycomb is, what that distance between the flats is. We got the 2/3 power, 3/2 power, modulus of the face sheet, and 0.75 factor. That's our dimpling allowable. And once again, we'd write our margin of safety by comparing our compressive stress to that value. If we're in compression, this would be valid for both face sheets. If we're in bending, it would only be valid for the compressive face sheet. Got that so far? Our next failure mode is column buckling strength. Now, this is one that we've been dealing with since our first structures class. This is analogous to Euler buckling. We look at the overall member and it goes into a buckle shape. The entire thing does. This is common when we have any kind of structural member that has some kind of constraint on the ends, but no constraint in between. And if its bending stiffness is not sufficient, and if its length is long, usually we call these longer columns, then it will buckle. Now, normally we get the Euler buckling allowable for this. Obviously, this is influenced by the bending stiffness of the overall sandwich, face sheet sandwich. It says face sheet sandwich, that's a typo. This is influenced by the bending stiffness of the sandwich. We take that D dimension, that D parameter, which involves the E, the modulus, and the I, the moment of inertia of the sandwich on a per inch basis. It's influenced by that. So the lower that value is, the lower that's what's resisting overall buckling. We could just write this as like an Euler buckling allowable, except that we don't have a homogeneous material. And so what we can do is plug in our dB equals I, EI parameter that we talked about in the last couple lectures, plug that into Euler's equation to approximate this. So using that approach, we would get our Euler buckling allowable like this, where K is our end constraint parameter. We take a look if we have pinned ends, K is 1, and we're back to Euler buckling. For any other value of K, I like to call it Euler buckling because it's not really Euler, but we've tweaked Euler's method to apply. So for fixed ends, you see K equals 4 and so on, different conditions. So you just plug in your K, you plug in your bending stiffness parameter D that we talked about last lecture, and whatever the effective length of that, the length of that column is. Not effective length because sometimes we use that term when we're burying that K within the effective length. We're talking the actual length with the K parameter to account for the end constraints. That's how you use this parameter. Now, and then our margin of safety would be written as that allowable against the actual compression in the thing. Now, the trick about this is there are a number of methods out there. Some of the books that I've given that I reference as other good composite books that you can purchase will deal with this in more detail and come up with more precise methods for calculating the precise buckling allowable. Since we don't actually have an isotropic material, we don't, a lot of times, we'll have idiosyncrasies of the sandwich and the composite face sheets that cause a little worse behavior. And some of those will allow you to select out the A terms and the B terms and the D terms out of the ABBD matrix to come up with a little better estimate. And all those methods are good, and sure, they're a great way to go. However, what happens is when we make things too complicated, you'll notice that all those cases are quite narrow in their application for like 1 or 2 little specific layups. And the engineer needs to be able to assess, not be afraid to assess, not be sitting there, well, I'm not going to evaluate this because I got no way to do it. The only ways I have only cover like these other things and mine isn't that. We need to be able to come up with an accurate an approximation that gives sufficient accuracy. And by using the D parameter in this Euler buckling equation, we can actually get a fair representation of any composite sandwich we might encounter. Now that is power. Now if we end up finding a reference with a little more precise equation for this, it's great and highly encouraged to go and use that equation, but don't forget to compare the answers back to this. There are 2 reasons for that. First of all, it's the more parameters you're dealing with, the more chance of making a mistake. This is true for students, it's true for industry, it's true for me, it's true for all of us. And so, and what happens is we get some kind of weird number. We don't even have a way to assess whether that's meaningful and correct or not. But by using this simplified approach, the calculations are quite simple. It's fairly straightforward to keep from having error-free analysis with just the error associated with the approximation we're making. And then if we go and try and use a more precise method, we can say, oh yeah, it's kind of in family. It's a little more different than I thought, but it kind of makes sense because I didn't account for this, didn't account for this with this approximation, and this is why this looks like a valid, better answer. Or if we can't seem to get that other equation to work in a way that makes any kind of sense, I recommend sticking with this as a likely more accurate method, unless we have vetted out that other equation and the implementation of it. So this is a great practical way that we can evaluate the buckling of sandwich structures. Okay. Our next one is core shear strength. Now this is pretty simple, but remember back to our model, we assumed that the core took all of the shear, the transverse shear. We presented last time that the shear stress in the core is just the shear force divided by the area, where we're using the HB dimension as our area and our margin of safety, then we'll be comparing the shear strength of the core to the shear stress in the core. So this FCS is the core's shear strength, and we'll look at that in just a little bit. Okay, next idea is crush. Remember, we have a core which is not as resilient. It gives nice uniform support to the face sheet, but it often is a lot spongier, has a lower stiffness than many isotropic materials we might otherwise encounter, metals and things. So let's say we have a little rod pressing down, or a foot pressing down on our sandwich. We can just take that area of contact, we'll call that A, and calculate the stress. Now, to use the area of contact with that force is probably a little bit conservative, because your load is going to fan out from the point of application. If your face sheets are thick, it may fan out a lot. If the face sheets are thin, it may fan out less. But it's straightforward and conservative and valid to just use that area of contact. P over A is that crush strength. Ignore the face sheets because they're likely not to fail, and check the core, which is generally the low stiffness, low strength member. So you take that, whatever the crush allowable is of the core, divided by that compressive stress. Now the next idea is similar, and this is the idea of punch-through strength. So once again, we have this, let's say we have a round rod and it's pressing against the core. If our core is strong enough in compression, it won't fail in compression. But it's still, that driving rod can push that face sheet right through the core if the shear strength is not sufficient. The way we evaluate that is take that force divided by the area that's loaded in shear. That will be the periphery around that rod times the thickness. Some folks use the core thickness, but it's probably better to use that H parameter, which is going from midplane to midplane of the face sheet. So we can write it for a round rod, we'd write it like this. If we have a non-round rod, we would just calculate whatever that periphery is and multiply that by the thickness, the H parameter, and then divide our force by that. And then we write our margin of safety by comparing the shear stress to the shear strength of the core itself. So we've got crushing of the core, which is using the area of the contact of the force, and the punch-through stress, which is the area around the periphery of that contacting member multiplied by the H. So two key parameters for evaluating sandwich structures. Okay? Let's look a little bit further on crushing of honeycomb sandwich, because this is such an important thing, and honeycomb provides a number of advantages for energy absorption, and so they're often selected for that purpose, and crush strength then is important to be understood. So if we have a sandwich, we're looking at H, that's the distance from top surface to bottom surface, that capital H dimension. As we compress it, we're going to start, what's going to happen is first it will just kind of elastically deflect a little bit, and then when the core starts to fail, it will start to cripple. If this is a honeycomb core, that super thin foil is going to crimple, kind of like crippling of thin flange members. It's going to crimple like if you take your aluminum foil and crush it or wad it all up like that. And what that's going to do is provide a nice uniform compressive stress. It's going to compress. Once it starts, it's going to be a nice uniform value of compressing. And it's going to keep compressing with basically a uniform value until it gets down to the solid height, when it's basically like shoved into a mass. Remember, there are a lot of voids in there, and eventually it will be roughly solid. And for many honeycombs, that's about 70-ish% of the total height. Okay, so that's kind of how through thickness crushing of honeycomb occurs. Okay, now when we're doing this, we can calculate the energy absorbed during crushing. Then, since we can expect the solid height for a honeycomb core to be about 70% of the full height, then that stress of crush, that's crush allowable, times that area of contact, times that 70% of H, this is written a little funny, but times 0.7 H is how much it's moving. That's the average energy absorbed during crushing. Okay? Now let's look a little further at this. how honeycomb crushes. What happens is when you crush honeycomb, you have something that, here's our compressive force on the vertical axis and displacement on the horizontal axis. And we can see that we start out by going up roughly a linear relationship as this core is compressed and it hasn't yet failed. Then you're going to get the start of that crimping, right? That was all at the first picture. Then you get the first start of compression. And as soon as that core starts to crimple into little like wadded up pieces, crinkle, it's going to immediately drop its load from that initial value down to some other value. And then it's going to kind of oscillate as different little parts of the core. So you're going to get a little pattern like this as different parts give a little more resistance, a little less, a little more, a little less, a little more, a little less. So you're going to see this linear relationship, which peaks out. All that is in the elastic range. And then you get failure starting. And when you do, you get a huge load drop. And then you get roughly nearly even hold of stress as that thing crushes. So you put a certain force on it. It's going to, if you're reading the force in your load machine, it'll be basically a constant force as that thing deflects until you get to that solid height, and then your load starts to go increase drastically quickly. So we're going to find a couple of these points. We're going to be looking at the stabilized compressive strength and what that crushing strength is. We're going to look at that in the next slide. The area underneath this curve is the energy absorbed, and we can approximate it with this equation that I gave here. These are out of Hexcel booklets, and basically all this ignores that initial peak and its influence on the crush strength. It basically takes that flatwise crush strength as if this immediately started to fail and just flatlined here. Okay, so this is what we showed last time. This is properties for one family of honeycomb from Hexcel out of their booklet, and we can see the different designations of core, and we're going to drill down on what this means, and we're going to look at what this means versus our core, versus our crush graph that we just talked about. Okay, so you'll notice there's a bazillion values here. We have the designation on the left, we have the nominal density of the core, and then we have all this stuff. We get all these different compressive allowables, bare and stabilized and crush. Who knows what that means? Well, that's what we're going to talk about. And then into the shear strengths, which we'll talk about next. So let's figure out what this means here. First thing we're going to do is look at this bare strength. The bare strength is if you had honeycomb with no phase sheets and you crushed it, that is the strength of that honeycomb. Just the honeycomb itself with no phase sheets attached. That's called what Hexcel calls the bare strength. They provide typically typical values and minimum values. And depending on your application, you could use either one. A lot of folks will just grab the minimum value. Some folks will use the typical value. Minimum's conservative. Okay, so that's that bare value, and that corresponds with that ultimate strength right before anything fails for honeycomb with no phase sheets. Now, as soon as you attach the phase sheets to it, they call it the stabilized strength. So if you have that same core and now you bond using the appropriate methods your phase sheets on, and then you compress it, you'll notice that you'll notice that honeycomb can no longer just crush and deform by itself. It now is stabilized by the phase sheets that are bonded. So that's called the stabilized strength. And that also corresponds to this point. Hexcel's data gives us both of these values, both the bare and the stabilized. And obviously, for any practical structural application, we're going to expect to use the stabilized values and not the bare values, since there aren't a lot of honeycomb cores flying without phase sheets attached. Once again, we're going to get typical and minimum values. I recommend using the minimum values for any application you have. If you're looking at an overall failure kind of strength, you might feel that a typical is more likely. And we also see the modulus here. So this is where we're going to get the modulus, that compressive modulus. That's what we're going to use for most calculations, will be this compressive modulus. Any calculation needing the compressive modulus of the material will use this stabilized value. There's one more value we have, and that's after we start to get failure of the core. Once the core begins to crush, you get this crush strength. So this, you'll notice here, if the core was by itself, we would have had a typical value about 950 psi for this first core listed. If it were attached to face sheets, that number would be a little better, about 50 psi better, be 1,000 psi typical. But once it starts to fail, it's going to drop down to 505 psi, and then it will hold that value all the way from the time it initially starts to fail until final crushing. The place we use this number is if you're actually designing for energy absorption by crushing core. Otherwise, we won't be using this number. We'll be using that stabilized typical or minimum compressive strength. You got that? So that's how we evaluate the appropriate core material, core allowables. So now let's look at the shear properties. Coming back to the same table, we'll start by looking at our callout. If you look at the designation here, you'll notice we have it, each core, honeycomb core, is called out by cell size, alloy, and foil gauge. So let's say we have the 1/4-5252-0007 honeycomb. That means that it's the cell size, the distance between the flats is 1/4 inch. It's a 5052 aluminum alloy. That foil is made of that. And the foil is 0.0007 thick. You'll notice we also have nominal density here, which corresponds with that callout. So we need to be able to recognize these and pull up the numbers. Now, different kinds of cores can tweak these callouts a little bit, so you need to be a little bit careful and read the data when you find the properties for the core you want. Now, we already talked about compressive strength, so now we're going to focus on shear strength. And in order to do that, we need to remind ourselves of how these things are reported. Remember, we have the honeycomb is laid out by taking the foil, attaching it together with bonding or welding in the ribbon direction, and then expanding the core into the shape, whether it's a hex or whatever. That's going to give us directional properties. We're going to have an L direction, and a W or widthwise direction, and a T or transverse wise direction. Okay, so those three values. Now, for plate, so you'll notice all of our compressive allowables for the transverse value. Okay, you'll notice there were no in-plane shear values for the core. The reason is the face sheet is much stiffer, and you can assume that all in-plane shear is taken in the core. What we do have here is a whole bunch of transverse shear values, strengths and stiffnesses for the core. Because when you have a sandwich and you load it, you're going to get perpendicular to chopping off the beam. It's going to be loading that core in shear, and those little thin ribbons of material are going to resist that in shear. Okay, so we're going to get different allowables in the longitudinal direction and the widthwise direction. Let's focus first on the longitudinal direction. You'll notice we have two strength values, the typical and minimum. Usually we're going to want to use the minimum for that. And we're going to have a modulus value, as you see here. We're going to use that typical modulus, and usually we'll use the minimum strength. Although, like I said, there are conditions where we might feel a typical value is more accurate for a particular application. In the widthwise direction, we have this typical, minimum, and strength, and then we have a modulus, typical modulus. Once again, we're going to use the minimum strength typically and the typical modulus. It's important that we pay attention to our ribbon direction and we align the strong direction with the direction of loading. You'll notice for our first material, the 1/16-5052-0007 material is a good deal stronger in the longitudinal direction for shear than the widthwise direction. So if you're doing making an application, you need to make sure that you align the longitudinal direction with your primary loads, the higher loads, so that you get a nice efficient design. So those are some ideas about how we can evaluate the strength of sandwich structures and therefore right margins of safety. I hope you find this useful. If there's anything, if you need to, go back and review that prior video that talks about stresses in more detail. Enjoy.